Hello everyone. So today we'll be talking about first order linear differential equation. So what is the first order linear differential equation? First order linear differential equation is a differential equation of the form dy dx plus py is equal to q, where p and q are functions of x but not of y. That is, p and q are plainly functions of x. For instance, 4x squared, 3x cubed over 2, 4 divided by x raised to the power 5 plus 5. So those are examples of functions which p and q could be. Or p and q could also be constants. P could be 3, q could be 2, and so on and so forth. So on multiplying both sides of this equation by e raised to the power integral of p with respect to x, we're going to be having e raised to the power integral of p with respect to x multiplied by the original equation on the left hand side, expression on the left hand side, that's dy dx plus py is equal to q multiplied by e raised to the power integral of p dx. So on doing that, if you look at this left hand side, this looks like the result of obtaining the differential of y e raised to power integral of p with respect to x. When you use product rule to simplify this particular expression, you are going to get e raised to power integral of p dx multiplied by dy dx plus py. That's what you're going to be having. Hence why we shrink it here. So the right hand side remains the same. I just rearranged it to give us q e raised to power integral of p with respect to x. So on doing that, we can integrate both sides now to obtain the value of y. So if you integrate the left hand side, we are left with y integral y times e raised to power integral of p with respect to x. And on the right hand side, we have the integral of q multiplied by e raised to power integral of p dx with respect to x plus c. So this particular solution we have here is the solution that is required of us for the first order linear differential equation we are given. Now, e raised to power integral of p dx, you must have been seeing it everywhere. We call it the integrating factor, and therefore we can rewrite the solution in terms of it as y multiplied by the integrating factor is equal to the integral of q multiplied by integrating factor with respect to x plus c. Now let's look at the working rule for solving first order linear differential equations. Now the working rule, the first one we are going to be looking at is converting the given equation to the standard form of the first order linear differential equation. That is, we express it in terms of dy dx plus py is equal to q. After which, we then find the integrating factor, which is e raised to power integral of p dx. Then at the end of the day, we obtain our solution by multiplying y by the integrating factor and equating it to the integral of q multiplied by the integrating factor with respect to x plus c. So this, we are going to show how this is going to work. So it might look kind of strange for now, but let's look at examples to buttress our points. So the first example we are going to be looking at is this. We have to solve the differential equation x cubed minus x dy dx minus 3x squared minus 1 into bracket y is equal to x raised to power 5 minus 2x cubed plus x. Now let's look at the solution together. Recall that the first thing we have to do is express the given differential equation in terms of dy dx plus py is equal to q. Now to do that, we have to divide through by x cubed minus x. So on doing that, we have dy dx minus 3x squared minus 1 divided by x cubed minus x into bracket y is equal to x raised to power 5 minus 2x cubed plus x divided by x cubed minus x. So we can further simplify the right hand side of this differential equation to give us dy dx minus 3x squared minus 1 divided by x cubed minus x multiplied by y is equal to, when we divide x raised to power 5 minus 2x cubed plus x by x raised to power 3 minus x, we are going to be obtaining x squared minus 1. So now this looks like the general form of the differential equation dy dx plus py is equal to q. You can see now that p is a function in x only and is equivalent to minus 3x squared minus 1 divided by x raised to power 3 minus x, and q is x squared minus 1. So the next thing is to obtain our integrating factor. Now to obtain our integrating factor is just e raised to power integral of p with respect to x, and that's e raised to power integral of minus 3x squared minus 1 divided by x cubed minus x with respect to x, which you can rewrite as e raised to power minus integral of 3x squared minus 1 divided by x cubed minus x with respect to x. So I'm using u substitution method. If we let u be equal to x cubed minus x, we have our du to be equal to 3x squared minus 1 dx, and hence dx will be equal to du divided by 3x squared minus 1. That's very straightforward. So our integrating factor is now e raised to power minus integral of 3x squared minus 1 divided by u multiplied by du divided by 3x squared minus 1. And we have that to be e raised to power minus integral of du divided by u. So on integrating that, we have e raised to power minus ln u. We all know that e raised to power ln a is going to give us a. So we can write this as e raised to power ln u raised to power minus 1, and that's going to give us e raised to power minus 1. Now we know that u is equal to x cubed minus x. So our integrating factor now becomes x cubed minus x raised to power minus 1, which we can now write as 1 divided by x cubed minus x. So we've done the second step. Now to write our solution. Our solution is of the form y multiplied by the integrating factor is equal to the integral of q multiplied by the integrating factor with respect to x plus our arbitrary constant. So we have y multiplied by 1 divided by x cubed minus x is equal to the integral of x squared minus 1 divided by x cubed minus x with respect to x plus c, our arbitrary constant. So we can factorize the denominator of this right hand side and write it as y into bracket 1 divided by x cubed minus x to be equal to the integral of x squared minus 1 divided by x into bracket x squared minus 1 dx plus our arbitrary constant. So this becomes y into bracket 1 divided by x cubed minus x is equal to the integral of dx divided by x plus c. So we now have y divided by x cubed minus x to be equal to ln x plus c. So we can cross multiply now. So we have y to be equal to x cubed minus x into brackets ln x plus c, which you can go on to expand it as y is equal to x cubed minus x ln x plus c into brackets x cubed minus x. And this is the solution of our differential equation. Now let's take a look at another example that we have here. dr plus 2r cos theta plus sine 2 theta the theta is equal to 0. So we know the first thing we have to do. We want to write this differential equation in the general form, which is I'm going to write it in terms of r and theta here now, which is dr d theta plus pr is equal to q. So this is what we want to write it as. So to do that, we have to divide all through by the theta first. So we have dr d theta plus 2r cos theta plus sine 2 theta is equal to 0. So we can take sine 2 theta to the other side in order to let our equation be of that form. So we have dr d theta plus 2 cot theta r is equal to minus sine 2 theta. So this looks like the general form of our differential equation where our p is 2 cot theta and our q is minus sine 2 theta. So now we have to get our integrating factor, which is equal to e raised to power integral of p d theta in this case, since our theta is the independent variable. So we have this as e raised to power integral of 2 cos theta d theta. So on doing this, our integrating factor is e raised to power 2 integral of cos theta divided by sine theta d theta. For the integral, we can see that we can use u substitution here. If we let u be equal to sine theta, then we know that our du will be equal to cos theta d theta. Hence, our d theta now becomes du divided by cos theta. So moving on, we have our integrating factor to be equal to e raised to power 2 integral of cos theta divided by sine theta d theta. And this is equal to e raised to power 2 integral of cos theta divided by u multiplied by du divided by cos theta. So we have our integrating factor to be equal to e raised to power 2 integral of du divided by u. And this is e raised to power 2 ln u, which is e raised to power ln u all squared. So on doing this, we have our integrating factor to be equal to u squared. And since our u is sine theta, our integrating factor is sine squared theta. Job done there. So next thing we have to do now is to write our solution. So to get our solution, recall that our solution is of the form y multiplied by the integrating factor is equal to the integral of q multiplied by the integrating factor with respect to theta in this case plus c. Now we have y sine square theta is equal to integral of minus sine 2 theta, which is q, sine square theta d theta plus c. So we can now further simplify it. Y sine square theta will be equal to minus integral of, we know sine 2 theta to be equal to 2 sine theta or 2 cos theta sine theta, then multiplied by sine square theta d theta plus c. So we have y sine square theta to be equal to minus integral of, minus 2 integral of cos theta sine cube theta d theta plus c. So using u substitution for the left hand side, we can make sine theta be equal to u. So our du will be equal to cos theta d theta. Hence, our d theta can now be equal to du divided by cos theta. We can use this to evaluate the integral. Y sine square theta is equal to minus 2 integral of cos theta multiplied by u cube multiplied by du divided by cos theta plus c. Sorry. So plus c. You can further simplify this to give y sine square theta to be equal to minus 2 integral of u raised to power 3 du plus c. So we have our y sine square theta to be equal to minus 2 u raised to power 4 divided by 4 plus c, which is equal to minus u raised to power 4 divided by 2 plus c. So our u now is equal to sine theta. So we have y sine square theta will be equal to minus sine theta raised to power 4 divided by 2 plus c. And this is the required solution of the differential equation that we were given. Let's take a third example. So our third example, it's kind of different from the ones we have been doing, but it applies the same concept. So let's see. We have 1 plus y squared dx is equal to tan inverse of y minus x dy. Okay, so our first task now is to rearrange this and rewrite it in the form of dy dx plus py is equal to q. So we want to write it in this form. To do that, I think we can divide both sides by tan inverse of y minus x multiplied by dx. And we're going to be having 1 plus y squared divided by tan inverse of y minus x is equal to dy dx. Now, looking at this equation, it's not an equation, it's not a differential equation that we can readily express in this form that we need it to be. So what then do we do? How about we consider x as the dependent variable and y as the independent variable? So let's rearrange, which means we want to write it in the form dx dy plus px is equal to q, where p and q are both functions of y alone or constants. So it's the same idea as the regular ones we've been doing, but in this case, x is our independent variable, is our dependent variable, and y is our independent variable. So now let's rearrange it in that form. So we have the x dy to be equal to tan inverse of y minus x divided by 1 plus y squared. Now we can rewrite this as tan inverse of y divided by 1 plus y squared minus x divided by 1 plus y squared. So let's take the x to the other side. We have dx dy plus x divided by 1 plus y squared is equal to tan inverse of y divided by 1 plus y squared. Now this looks like the desired form, dx dy plus px plus q. And we can see from here that p is 1 over 1 plus y squared, and our q is tan inverse of y divided by 1 plus y squared. So the next thing is to find our integrating factor. Our integrating factor now is e raised to power integral of p dy. Since y is our independent variable here, so we have e raised to power integral of 1 divided by 1 plus y squared dy. And this is going to give us e raised to power of tan inverse of y. So this is our integrating factor. The next part is to obtain our solution. So our solution is of the form y multiplied by the integrating factor is equal to the integral of q multiplied by our integrating factor with respect to y in this case, plus our arbitrary constant. So now we have y multiplied by e raised to power tan inverse of y is equal to tan inverse of y divided by 1 plus y squared. Oh, I forgot the integral. Divided by 1 plus y squared multiplied by e raised to power tan inverse of y with respect to y plus c. Now, on making u to be equal to tan inverse of y, let u be tan inverse of y. Then we have the u is equal to the y divided by 1 plus y squared. So our dy now becomes 1 plus y squared du. So in continuation, we have y e raised to power tan inverse of y is equal to the integral of our tan inverse of y is now u divided by 1 plus y squared multiplied by e raised to power u, then dy, which is now equal to 1 plus y squared du. So now we have y e raised to power tan inverse of y to be equal to integral of u e raised to power u du plus c. So we now evaluate the integral of u e raised to power u du using our integration by parts. So here, on evaluating it using integration by parts, we have integral of u dv is equal to uv minus integral of v du. So this is our formula for integration by parts. On applying that, we have the integral of u e raised to power u du to be equal to u e raised to power u minus the integral of e raised to power u multiplied by du. So on doing this, we have integral of u e raised to power u du is equal to u e raised to power u minus e raised to the power of u. So now we can recall that u is equal to tan inverse of y. So integral of u e raised to power u du now gives us tan inverse of y multiplied by e raised to power tan inverse of y minus e raised to power tan inverse of y. So back to our equation, we have y e raised to power tan inverse of y is equal to the integral that we have. We've obtained the answer to be tan inverse of y e raised to power tan inverse of y minus e raised to power tan inverse of y plus c. Sorry, not x. We've been using x all the while. So to change that, so I've adjusted it. I mistakenly wrote y here initially. So it should be x. Since our x is the dependent variable here now, so it becomes x e raised to power tan inverse of y. Likewise here and in this place. Also in our previous page, I already adjusted it to be x instead of y. So sorry about the mistake. So in continuation, we can divide all through by e raised to power tan inverse of y. So we have x is equal to e raised to power minus tan inverse of y multiplied by tan inverse of y e raised to power tan inverse of y minus e raised to power tan inverse of y plus c. So we now have our answer to be x is equal to tan inverse of y minus 1 plus c e raised to power minus tan inverse of y. So this method is a very straightforward method as long as we are able to organize our differential equation or in the form dy dx plus py is equal to q, or it could be dx dy plus px is equal to q, just like the example we just saw right now. So with this, we've come to the end of this video, and I hope you guys enjoyed watching this video. Thank you very much for staying tuned.